Assalamualaikum warahmatullahi wabarakatuh and greetings all. Now, finally, we arrived to the final part of EMT, which is the time varying field. The time varying field will cover two chapters. The first chapter is chapter 10. We will discuss something about the Faraday's law, displacement current, as well as Maxwell equations. And then the last chapter is chapter 11, discussing the wave propagation as well as Poynting vectors. The course objective, firstly, to identify the difference between the static field, electric and magnetic field with the time varying field. So what we covered so far is time invariant, and now what happened to our E field and H field for time varying field. Second, to exhibit the phenomena whereby the current is produced by time varying magnetic field, for example, Faraday's law. So for the second part, we will see how can we generate a current in a circuit without any source, but the circuit is exposed inside the magnetic field. Whether the magnetic field is time varying or time invariant, we have a certain condition how the current can be produced. And third is to investigate the chains of Maxwell equation for time varying field. So what we see so far is Maxwell equation for time invariant field, and then we have to alter the Maxwell equation to satisfy the time varying field. Okay, we have two parts here. The first is field is independent with time. This is a time invariant field. For the static charge E, we call an electrostatic field. We already see this part. And then when we have a moving charge with a constant velocity, so we call this as a magnetostatic field. Alright, the second part, which is a field is dependent with time t, this is where our last two chapters covered. Time varying current is also known as EMT field, electromagnetic. For example, in Cartesian coordinate, we can see that the E field has the extra component, which is time. And here, the E field and H field always depend on each other. Is there an E field, there will be H field. And this is another explanation. We have the field is independent with time, and then we have the field dependence. So here we only have a XYZ components for both E field and H field. For here we have another component, which is time. Okay, that is only the difference. Okay, two important issues in time varying field. First, we have the Faraday's law, and the second part we have the displacement current. So these two things will be used to in modification of Maxwell equation for the time varying field. Basic discussion on time varying field will be based on Faraday's law. So what Faraday's law say about this? Faraday's law states that the generation of electric current due to time varying magnetic field discovered by Michael Faraday. Okay, this is, if you see this figure, we can see that when we have the first circuit will generate the current, and the current will produce the flux, and then the flux will link to the second circuit, where this circuit does not have any electrical source, but you can see at the second circuit the current can be produced at a certain condition of the magnetic field. Okay, from the experiment, three observations have been deduced by Faraday. Firstly, when the battery is turned on, there is a deflection in the galvanometer. Second, when the battery is turned off, there is also a deflection in galvanometer, but an opposite direction from 1. Later demonstrations show that a moving loop would also cause a deflection in galvanometer. The conclusion from this experiment is Faraday mentioned that the electromagnetic force EMF can also be explained by Lenz's law, which is the time-varying magnetic field produces an induced voltage in a closed circuit opposite to the flux producing it. If you can see from these expressions, you can see that the VEMF produced in the secondary circuit is always negative to the linkage plug. Okay, that means the VEMF produced will always oppose to the flux producing it. Let's say at the region there is a magnetic field. When the magnetic field produce the VMF, and VEMF will also produce the induced current, the induced current will always oppose to the flux producing it. It will try to maintain the original state. It's just like an inertia. When you are moving and suddenly you stop, so your body is still want to move. And vice versa. It's try to maintain the original state. This is what Lenz's law is all about. So what is the expression mean about the VEMF equal to negative d lambda over dt equal to n d flux over dt. Okay, this is a n. Normally we shows to the number of a loop. Okay, and this is a flux magnet produced by the system. Okay, this is equal to the B, the flux density passing to the surface. Okay, ds. I think you already see these formulas. Alright, we also call the VEMF as a electromotive force. Right. This is the graph for lambda, the linking flux. So when lambda is positive or increasing, the VMF will be negative. When the flux decreasing, the VMF will be positive. You can see that the increasing of flux, so the VMF will try to oppose it in the opposite direction. So it will try to maintain the flux. Alright, so we will see three valid conditions for the analysis of Faraday or Lenz's law. The condition is, first, we have the static circuit in time varying field. So the circuit is not moving, but we have a time varying field. Or we call this as a transformer EMF. Okay, this also can produce the VEMF. The second condition is moving circuit in the static field. If we have the time invariant field, so it can also produce the induced current if we move the circuit. Okay, the circuit is moving. And the third condition, if we have moving circuit in time varying field. So basically for the third case, it's just the combination of the first and second case.